Welcome, everybody. I hope my mic's coming off. I've been having a little bit of fit with it tonight already. Am I loud and clear?
Yeah.
Yes, you are.
So, welcome to the November meeting of Tucson Amateur Astronomy's Fundamentals Group. For those who are joining us for the first time, and I see a couple of names I don't recognize, this meeting typically has a format where we have two presentations. One is has been bouncing back and forth between a notable astronomer of the month, or as we are doing this month, we are detailing a constellation of the month. Yeah, and then in addition to that, we also have a main topic that is generally a little bit more in depth than the other two. And tonight, that will be Doug Smith, who will be presenting on the history of astrophotography, who will be going first. And then after that, Pete Hermes will be presenting on the constellation Aries, I believe. If I got that right. I can't remember what I put in the agenda now. It's been a while. So, Doug, on you go.
Pisces. It'll be
Pisces? It
Pisces.
was Pisces. I couldn't remember Pisces series. Thank you for correcting. I've,
Nothing makes a difference.
it's been a long week.
They're right next door to each other, okay?
They are. They are. Doug, so go ahead and take the screen share on your go.
Okay. No, not that one. This one. Okay. Oops. Okay. Okay. Can everybody see that?
Yes. Yes, we can.
Okay. So this is a repeat of a presentation I did, as it says there, back in July of 2018, but I figure it was time to repeat it since we had different people in the group and not everybody saw this the first time around. So surprisingly enough, when I did the research, what I found is that the history of astrophotography, no surprise, actually followed the history of photography pretty closely. Um, Basically, every time there was a new development in the area of photography, it was quickly adapted to astrophotography, which I found interesting. Although in some cases it wasn't practical, as we'll see. Um, so if we look at photography, it goes through a number of steps. There's what you call the pre-film era, if you like, which the first photograph was what was first photographic process was called the daguerreotype, after a Frenchman who invented. And then there was something called the collodion or wet plate type. And then there was what was called the dry plate or gelatin. Now, those were all done using glass plates and things like that. And then you got into what we call the film. And I like to call, there's a period of astrophotography using film that I call the golden age. Um, Not because it's necessarily that great, but it was really spectacular for a while before we got into modern imaging techniques with CCD cameras and things. So the daguerreotype was actually first invented in 1839 by Louis Daguerre, Frenchman. And he discovered that certain silver halide crystals were sensitive to light, meaning that they would change their properties when they were exposed to light. And what he found was that he could take a plate made of silver or copper or brass or something like that, and using a variety of really nasty chemicals like halogen, iodine, bromine, and other things, he could form a silver halide layer on this plate. And then if this plate was exposed to light, it would actually form an image in that layer of crystals. And then he would use some other really nasty chemicals like mercury fumes and other things that would fix that image so that it would be long lasting. And he would protect the image by covering it with glass plates. And that's was the original daguerreotype process. And nasty chemicals were used. Um, this is the earliest photograph I could find. This is a daguerreotype image. It's out of Daguerre's study, actually, in Paris, and it's dated 1839. And the exposure time here was 12 minutes. Um, as a result of that, you don't see anything on the streets. Everything that moved, people walking, horses, horse-drawn carriages that were moving, in 12 minutes, they're gone. So they don't show up in the image. The only thing that you see in the image, it's down there, right down here. There's a man standing there getting his boots polished. And you can see the man and the guy who's polishing the boots. That's because they stood there long enough, 12 minutes, to be picked up in the image. This is the earliest photograph I've ever seen. Now, needless to say, 12-minute exposure just to get that kind of a street scene means it's not very useful for astronomy. Um, I mean, imagine trying to take a dark sky image, sitting there for hours, and there's no telling what you'd get. Also, there was no way to reproduce the images because they're on a copper plate. How do you reproduce it? So that was a problem. And also, the toxic chemicals, obviously, nasty. I'm sure some people died from breathing in the fumes while they were processing these images. Still, I did find this image. This is a daguerreotype image. This image was taken during the solar eclipse on July 28, 1851. I don't know how they did it, frankly, to be honest, because there isn't that much light, I would think. But I found it. This is a really old image. Then there was a big change. There was what was called the wet plate process was invented. This came out just about the time of that solar eclipse picture, a little afterwards, 1851. And here, the silver halides are in a solution form, and you would use a glass plate instead of a metal plate. And you would pour the silver halides over the plate and then expose the plate to the light, and then you would develop it and fix it and do everything else. This was the process that what's his name, Brady, used during the Civil War to take all the well-known Civil War photographs, like that one there. Lincoln, Grant, and Sherman together. This was the process that Brady used for all his Civil War photographs. Now, the problem with this process, though, there were advantages over the old daguerreotype process. The big advantage was you could make your silver halide solution ahead of time and store it in a large batch in a big bottle or something. So you got very consistent results because you could use this a constant mix for mixing your silver halide. You got much faster exposure times, seconds instead of minutes. You didn't have to have people standing there for an hour. You could actually take their picture in a few seconds. And since the image was on a glass plate, you could reproduce the image again and again and again. And thus you started to see pictures in newspapers. Brady's pictures of the Civil War started showing up in the newspapers. Now, the disadvantage, which makes this also not a very good process for astronomy, You had to prep the plate, expose the plate, develop the plate, and fix the plate all before it dried. So you didn't have much time. You typically only had 10 to 15 minutes to complete the entire process. So again, for the purposes of astronomy, it means you can't do long time exposures, which means deep sky objects are out of the question. You could do the moon. Here's a here's a wet plate image of the moon. I didn't know the exact date, but I was able to get it down to, it was somewhere in 1860. That's not a bad picture of the moon. And finally, 1871, a gentleman named Richard Maddox figured out that he could take the silver halides and suspend them in a gelatin that could be applied to the glass plate. And that's what's called the emulsion layer. Um, it was extremely delicate and easily damaged, so the plates had to be handled very carefully. But now you could create an emulsion layer on your plate and store your plate for a very long time as needed, and that made things much easier. A few years later, another chemist named Bennett discovered a way of hardening the emulsion so it wasn't so delicate. And then in 1878, he discovered that the sensitivity of the emulsion layer could be enhanced by heating the emulsion prior to putting it on the plate. So that was nice. And then finally, 1879, a name by the name of George Eastman developed a machine to coat the plates and open the first dry plate factory and founded the Eastman Film and Dry Plate Company, which we know of today as Kodak.
Doug, you have a question from Pete.
Go.
Hey, Doug, this may be kind of silly. The first wet plates.
Yep.
How runny was that liquid, or how viscous was it?
Um, well, I've touched a few wet plates actually. I've done this wet plate.
Okay, so they didn't have to like lay the plate horizontal and use mirrors to project the image then.
No, no,
They could
no.
do it vertically. Okay.
The silver halide solution was fairly thick and viscous.
Okay. That's all.
You
Thank
could
you.
and even if the solution ran down the plate, there would still be a layer on the plate, a thin layer, but there would still be a layer on the plate that would last for a while. And
Okay.
that's what I mean. You'd get like 10 to 15 minutes before the plate would dry.
Okay. Thanks.
Okay, where were we? Oh yeah, Eastman Kodak. Okay. Um, it, so this revolutionized photography, obviously, because now you can buy your plates from a pre-processed factory, and they're all made exactly the same way in the factory. So very consistent results. You could store them in a box, like that box that's there, and they made dry plate cameras, what you commonly think of as a box camera. There's a picture of it down there in the lower right. And so now photography became something that I wouldn't say the ordinary layman on the street could do, but that you started to have professional photographers doing work. And you started to get labs. There would be labs around that could process these plates. You'd take them in and they would do all the processing for them. So this became something of interest now in terms of a hobby. Um, that series of photographs down at the bottom is very famous. I remember seeing a TV special on BBC about this. Um, this was really the first big use where the dry plate camera was actually used for something other than a hobby. It was used in a big way to make a big bet. Two horse racing enthusiasts who were millionaires made a bet against each other. One of them bet that when a horse was at full gallop for a period of time, all four legs were off the ground for a split second. And the other man said, no, that's impossible. And so what they did was they put a line of cameras on a track, like a few yards apart, and had strings going across the track that would trip the shutter on the camera. And they had the horse run through at a full gallop, and they got this series of pictures, and it proved the one man was right that for a short period of time, all four legs are off the ground. I think you see that in the fifth frame on the top row. All four legs are up and off the ground, and the fourth frame looks like they're off the ground too. Um, and This is the first inkling of motion pictures, because now you could take these pictures, and if you run them through right real close to each other, it looks like the horse is running. Astronomers were quick to jump on the bandwagon. Once we started getting dry plates, we could start thinking about exposing them for long periods of time. That image up in the right is the first astronomical image I could find, the earliest, taken by Draper. You've all heard that name before. He took that image in 1880, and that's of the Orion Nebula. Doesn't look very good by today's standards, but 1880 now, we're talking 150 years ago. Then 1883, an astronomer named Andrew Common took that image on the lower right. And what he proved with that image is that the film could pick up more than the naked eye could. Because that image at the bottom right, I mean, you don't see that with the naked eye. That's actually a pretty good picture of the Orion Nebula. Um, the astronomers, like I said, they jumped all over this. They started, I mean, all the old observatories. If you go to Lick Observatory or Yerkes Observatory, even Mount Palomar, they all got their own dark rooms. I mean, they would do all the processing on the plates themselves. Um, when I was in school, I don't know if this is true today, Connor, you could tell me. Um, when I was studying my PhD in astrophysics, we had to learn how to develop glass plates. Did you have to do that?
I did not take an astronomy degree, but I
Oh,
do know that the
sorry.
U of A no longer offers this sort of course in their material because everything is digital. There,
Yeah.
I think they retired it in like the mid 90s.
Okay, I believe it.
It's
Um,
like even like the mid 80s, most astronomy was done in digital form at that point.
yeah, okay. So I was in school in 1978 when I did that. So they were still using glass plates. Now, mainly back then, um, by that time, glass plates were not used for deep sky photography, but they were still commonly used for spectrum. Okay. And so that's what we learned how to do is take a spectrum on a glass plate. And then they went out and created large, very expensive machines for measuring spectral lines and things. And they were called, what are they called? There it is down the bottom, microdensitometers. Um, that's a picture of one down the bottom right, 1975. And the only purpose of that machine, its sole purpose, is to measure the spectral lines on a spectral plate to measure their location, their density, and all the other information about it. And that was the sole purpose of that machine. So you probably don't see those machines anywhere. And those things could run, like I said, $100,000 in 1980, and every observatory had one back then. Um, here's a All right, so this is going to be tricky because what I did the first time I did this presentation, I had glass plates that I passed around. I'm not going to be able to do that, but I do have some glass plates here that I think I can show. No, I can't. I can't show them. I'll show them after I get out of the presentation. I can put them up to the camera. Okay. But that bottom image is glass plate spectrum of some stars. Now, one of the problems with photography, for those of you who did film photography or may have done back in my days glass plate photography, is you had a problem called reciprocity failure. This is not a problem with digital photography. You have other problems with digital photography, but this was a problem with reciprocity failure, with with film emulsion type of thing. The problem you would have is, for example, if you have two stars, A and B, and star A, let's say, is twice as bright as star B, you would expect that you would have to expose the film for star B twice as long as you would for star A. Turns out film doesn't work that way because it's a chemical reaction with the individual granules of the silver halide crystals. They require a certain number of photons of a certain amount of energy in order to make that chemical change to go from unexposed to exposed. And unfortunately, it's not a linear relationship. If it takes too long, then it's what's the word I want to use? Not cumulative. If 10 photons hit it in a minute, you might get the reaction. But if the 10 photons hit it in 2 minutes, the reaction may have already turned off because the photons are coming in too slow. So you have this nonlinear relationship. A lot of times to gain one magnitude in exposure, which is normally about 2.5 times difference between magnitudes in terms of luminosity, you actually might have to expose the film for 4 to 5 times as long. And they also found that reciprocity failure gets worse as the film gets faster. So that was a problem because astronomers, you want the fastest film you can get because you want to shorten the exposure time. But the faster the film, the worse the reciprocity failure usually is. So that was you're doing a trade-off every time I remember this when I was shopping for film to take my pictures that I took with my 8-inch Schmidt, 35, 40 years ago when I was doing photography with film. I remember doing this trade-off. Do I want film with an ISA of 2000? The reciprocity failure is terrible. Or do I shoot with something that may only have a ASA rating of 500, but has better reciprocity results? You do these trade-offs when you buy the film. So that was always an issue when I went shopping for film. Oops, too far. And then, of course, at very low light levels, the film is usually very less responsive than at higher light levels. I mean, that's obvious. It takes a certain number of photons to trigger the reaction, and if you're not getting enough, you're not getting it. Yeah, okay. So like I said, if you're not getting enough photons in enough time, the reaction actually goes backwards and you lose your image, so to speak. So you have to, that like I said, you have to fight this battle all the time with film. 1940, Kodak, specifically at the request of professional astronomers around the world, said we need films that don't suffer from reciprocity failure. And Kodak developed a series of films. They were called the 103 series of spectroscopic films. The 103A, because it was the second series that Kodak tried to develop. And there was an AF and an AE and an AO. And each of the films had a peak response at a different wavelength of light. And so they were you could take images with 103 AF and you'd get one spectral line like red or something. And then you could do AO and you'd get everything in the blue or something like that. Well, the nice thing about this is first, there was almost no reciprocity failure. Not quite zero. There's no such thing as zero. But they were very low in that specific wavelength. The reciprocity failure was practically zero. Um, and it was very linear. In that one wavelength that the film was made for, you got very linear results. If you wanted to get a star that's twice as bright, you only had to expose it for half as long. Very, very linear results. Uh, they were available in dry plate format and they became available in film format later in life. They were expensive. I bought a roll of 103A film once, a 35 millimeter roll of 20 exposure, and it cost me like $50. And this is back in the 70s. Expensive stuff. But the 103s became the workhouse for most professional astronomers until the invention of the digital cameras. Um, the Palomar Sky Survey was done using the 103s. Um, and they did two plates. They did a red plate and a blue plate. And what that allowed them to do was they could do what's called a B minus V calculation. So they could get the spectrotype of every star from doing the subtraction of those two plates. They could match that up with a spectral type. This is an example of this is M81 out of the Palomar Sky Survey, which was done using the 48-inch Schmidt camera telescope on top of Mount Palomar. And this is one of the images from that sky survey. And like I said, eventually you could get the stuff in a roll form, very expensive. And then Kodak ran into, quote, financial hardship because of digital photography. Um, and unfortunately, with the digital market hitting the professional observatories and professional astronomers, there wasn't a need for the specialty films anymore. So Kodak stopped making the 103s. And now the only thing you can get from Kodak is your basic films.
Hey, Doug,
Yeah,
does that type of film have a shelf life?
that's a good question. I don't know the answer to it.
Okay.
I when I was in an astronomy club in Detroit, we kept some 103s around for a number of years. You had to keep it cooled.
Okay.
You had to
It was
keep
sealed, of course, right?
you had to keep it chilled.
Yeah. But
And
I mean,
now,
each of the cartridges were sealed. Yes.
well, they were standard 35 millimeter
Okay.
rolls, but you had to keep them. You kept them in their little plastic container with a lid on it, and you kept them in the refrigerator to keep cold. But I remember some of those being in there for years,
Yeah.
and they still worked fine. So these emulsion layers that they put on films are pretty stable. I'd love to get a hold of that stuff. Can't find it anymore. Um, okay, so by the early part of the 20th century, Kodak had obviously introduced black and white film, but they also started coming out with color films on a substrate that they could put on a film. It didn't have to be on glass plates anymore, so they could put it on a film. Um, early films were pretty slow. ASA of 64 for Kodacolor. Um, Not very well suited for astronomy because that's pretty slow. By the 60s, everybody, scientists, artists, photographers, everybody wanted faster and better quality films. And you had dozens of companies pop up making films. Um, that's why I call this the golden age of photography. I call the 50s and the 50s through to the 90s because there were lots of films out there from many different companies, including many, many really good films for use in astronomy. I tried a whole bunch of them. This is an example of some of them. Um, Kodak made a film with an ASA of 400, which was pretty good. They actually made a Kodacolor with an ASA of 1,000, which I thought gave really good results. Um, Fujifilm, this one up here, had an ASA of 1,600. And I got some nice photographs with that. These films did not suffer too much reciprocity failure. Some of them did, but some of them didn't. Some of them were better than others. Kodak had this film called technical pan film. I don't know if any of you ever remember using that. Um, the ASA was very high. Now it's black and white, but it had a very high ASA. So if you don't mind black and white photographs, it was really good for astrophotography. GAF 500, which was a common film for a few years in the 80s. And GAF also made a 200 and a 100, I think. Turns out the GAF 500 was a pretty good film for astrophotography. I took some nice images with that. This one down here in the bottom right, the Ilford, whatever, Delta, um, color film, ASA 3200. Bad film. Suffered reciprocity failure really, really bad. I tried one roll of it and said, "Oh, I can't use that." Um, but there were lots of films. And they were cheap. You could buy them just about anywhere. And most of the processing shops um, could process these films because they were commercial films, so they didn't require any special processing, which was nice. You could take them to the photo place in the mall and just drop your roll off, go shopping for a half hour, and go pick up your pictures. So that was kind of nice. Like I said, you had a high range of choices. You could go black and white and color. So that's why I call that the golden age, because I thought that was an easy time to do astrophotography. This is an image I shot. Fuji 1600, 25 minutes. Lagoon Nebula. 30 minutes. Kodacolor, ASA 1000. 30 minutes with the Fuji 1600. 45 minutes with a film company called Previa, which didn't last very long, which is too bad because I like this picture. 1600. I'm sorry, the Ilford 3200. I made a mistake. I said it was color and bad reciprocity failure. I got it mixed up with a different one. The Ilford 3200 is a black and white film. And this is an image I took with that. 20 minutes. This is Omega Centauri. And just a nice color picture, Kodacolor 1000, 25 minutes. The Kodak films, what I found, had really good colors. I love the colors in this picture. They're really nice. But here's the example of the reciprocity failure. Okay, it's the Konica 3200. Here's a film. This is the one I threw out, the film. This is a 3200, so it's very fast. Same exposure time as that, well, almost 25 minutes, 20 minutes of the nebula, but the reciprocity failure is terrible here. The red is not suffering much from reciprocity failure, but the blue is right out, is gone. You've lost it. That's not a terribly good picture. At least it's not very pretty. I don't like the red. But so I experimented with a lot of the different films that were available and tried to find what I thought was the best ones and the worst ones. So yeah. And now we come into the digital age. Um, I'm still learning about digital imaging. I'm not going to have a whole lot to say here, a few slides. A lot of different type of digital cameras. Um, Full frame digital cameras are still pricey. I don't think they cost $6,000 anymore, do they?
It can depend.
Okay,
Very much depends. I
okay,
would not be shocked by that price on some of the more advanced models. I think there's
okay.
also some full frame astrophotography cameras that go for
Well,
like four or 5,000.
I bought a full frame DLSR recently. I paid about 2,500 for it. That was several years ago. I gotta believe prices are a little bit lower today. But yeah, you can spend as much money as you want or as much money as you don't want to spend on these things. Um, Here are some examples. I've got that little imager on the left. That's a planetary imager. It's not much use for anything else because the chip is really, really small. It's like a quarter inch by quarter inch. I'm not even sure it's that big.
I got
Uh,
that one too, Doug. It's fun to play with, though.
it's fun to play with, and you do get decent planetary
Hmm.
images with it. I
Yep.
was surprised by that. Um, and then I bought a camera like the one in the middle. I didn't buy that exact one, but it's very similar to that. I bought Meade Deep Sky Imager, which is about the same as this Orion guy in the middle. And I paid a few $100s for it. And then I did buy a DLSR. Um, and actually, okay, so I paid $1,000 for it. Oh, I thought I paid more than that. Okay, and it's a Canon. And that's the DLSR I bought was a full frame. So the chip is the same size as a 35 millimeter film frame. And that's what you're paying the money for, is you're getting a much bigger chip. And as the chip size goes, so does the price. Um, these are some images I shot with that little dinky planetary imager camera. Really not bad. I mean, that moon image was the first image I took with it. And it's like, oh, that's actually a pretty decent image of the moon. And then the Mars image was surprising because you don't see that much detail through the eyepiece. Definitely. With an 8-inch telescope. You aren't gonna, I don't think you're gonna see that through the eyepiece. And then Jupiter and Saturn, hey. Um, my deep sky imaging camera, the one that I bought from Meade for a few $100s, it does not have a very big chip. It has a pretty small chip. So while the image of the Ring Nebula is not too bad, the image of Orion is terrible because it's such a small chip. You're only getting the core of the nebula. Most of the nebula is outside of this picture. Um, it's because it's such a small chip. You're only getting a little area. Um, and also, I noticed that when you stack frames, if there's any image drift between your stacked frames, you get areas where you lose the image. On the far right, you notice there's a bar here that's all black. That's where the stacks didn't line up, and I lose that.
Hey
So,
Doug,
yeah,
when you shoot this photography, whether it's black and white or color, can you tell us what type of mount you're what's associated with your camera? Are you
uh,
mounting it on like a clock
yeah,
drive
I
or?
can. I got a picture of that actually. Let me see. Go ahead. Let me jump ahead. There's my mount. So what I would normally do if I'm doing photography, this is my telescope. It's on an equatorial mount. Um, and the guide scope, that's the little guy on top there. That's marked guide scope. And then I would mount the camera right here at the prime focus of the telescope. Right now the camera's sitting over here on the table, but I would put the camera right there at the prime focus of the scope.
Although it's worth noting here that Doug is using specifically a wedge equatorial. The vast majority of astrophotographers today are all on German equatorials.
Right. Sorry. So it's an equatorial mount driven, and I guide it using the guide scope on top.
You're still doing manual guiding? I'm impressed by
Yes,
your
I
dedication
am.
there.
Yes,
I
I
can't do
am.
that. I can't sit there.
I have the patience to do it, having done film photography for many, many years. I think guiding by hand with digital is going to be a lot easier because the exposure times will be shorter. Um, yeah, so you still need to guide, but I mean, the exposure times with digital cameras now are probably a lot shorter than they are with film. I mean, I would imagine that, some of these images that I showed with film where I was taking 30 minutes, you could probably get today with just a few minutes. So that's going to make things better. Um, uh, and I had a slide in here talking about illuminated reticle eyepieces. If you're guiding, you need an illuminated reticle eyepiece to use. I don't like
Specifically
what
here, if you are manual guiding, auto guiding does
manual
not require
guiding.
this.
Sorry.
Just want
Yeah,
to be
if you're
specific here for those
manual
not
guiding,
familiar with guiding itself,
if
which
you are
has a whole separate.
manual guiding, um, I don't like the ones on the top because they only have a single hair in both directions. And if you put your target star right where the crosshairs are, you're actually blocking it out, so you might not see it if it moves. So I always use these ones that have the double crosshairs like this, and I center the guide star right in the middle, kind of. And they make a lot of those. And like I said, my guide scope, there it is. It's an ETX 90. It's got a pretty long focal length, which you want because you want to magnify your guiding image, what you want magnified a lot so that you can catch the movements before it affects the film or before it affects your digital image. So
Just to also continue iterating here, that with if you're doing auto guiding, the equation changes. You don't
yeah,
necessarily need nearly as much of a high magnification just because it has a
right,
lot
because it'll
better.
pick up the individual pixel changes.
Yes, but
Yes,
for manual guiding,
sorry.
if you do want to go that route, which props to you if you do, uh, won't not my cup of tea, but you would want, as Doug suggests here.
um, I use a barrel when I'm doing my guiding to even magnify the guided image even more. But that's just me. Um, Now I guess you can use this with auto guiding too, right? Off-axis guiding.
Yes, I do
Um,
off-axis guiding myself.
okay, I'm not a big fan of off-axis guiding. My
It's
problem with off-axis guiding, now this may be more true for manual guiding than auto guiding, is with the off-axis guiding, what I always found when I tried to use it for manual guiding was A, you you have to find a guide star that's bright enough for you to guide on. And that might be hard. The field of view that you're looking at, if you're looking at some nebula or something, there might not be any guides, there might not be any bright stars in the field of view. So that could be a problem. The other complaint I had is this mirror, this little pick-off mirror right here, is very small. And essentially, that's the size of your telescope that you're using to do your guiding with. So all of a sudden, the image of the star, when you get a guide star in there, it's big. It's not a little pinpoint image like the camera is saying. It's actually a big, a much bigger image, which I hated. That to me, that made things worse. And secondly, you're actually blocking some light from getting to the camera. I didn't like that either. So although I have one of these because it came with the telescope when I bought it, I've never used it. But for digital photography, like Connor said, the equation may be totally different because the digital photography with your auto guider camera hooked up, the auto guided can probably pick out a guide star or I don't know, is it guiding on the whole field of view? I don't know.
no,
Does it pick out a guide star?
You can it you so many of the drawbacks you last listed still hold true. You still have to deal with, finding a guide star, so you will have to rotate the whole guider occasionally
Right.
depending on your
Oh,
target.
okay.
Um, the concern of the prism blocking your primary image is generally not a fault of the guider, but a fault of you picking an image sensor that's too big for your guider.
Oh, so if you
So
use
if,
this, you might not want to
yeah,
go with a full frame.
yes. So for example,
Ah,
I go with I both of my cameras are standard APS-C crop sensors, and so they do not, if you when you orient the sensor, it does not intersect with the prism, and so you do not have that issue of it clipping into the frame.
interesting. I never even thought about that. So what? Yours is like a half frame?
It's like 70, like like 75%, I think, is
Okay,
APS-C
so
is.
that in area, it's half the size of a regular frame in area. Okay. Oh, interesting.
So,
Wow. I never even thought about that. You're right, though. Yeah, if you use a camera with a smaller frame,
but
you could
it is
orient the
definitely
prism so it
a,
didn't interfere with the image. Good
yeah,
point.
but it is definitely one of those you would do with auto guiding. But
Gotcha.
it still will be much more finicky than doing piggyback guiding.
Yeah.
But the benefits of off-axis guiding, especially at very long focal lengths, outweigh the trade-offs there.
I understand. It's the time issue. I get that.
No,
I mean, I did try using this is the one I have over here, this one on the left, because it's a Meade scope and this came with it. I got this guy here and I did take an image with it once. And sure enough, you could see right at the top of the image, the little area cut out where the prism was. And I said, oh, don't like that. But yeah, interesting. I never thought about that. Use a camera with a smaller chip, and you won't. Okay, interesting. Um, but I'm not a big fan of using these things. To me, they're just too hard to find the guide star. That's a lot of trouble. It seems like um, in
it
my
still will
rig,
be, but no matter which.
like this, the guide scope doesn't have to point anywhere near where the main scope is pointing. I would just center the main scope on the target and then look through my guide scope, which has a finder on it. My guide scope has a finder on it. Look through guide scope finder, and if there's some bright star nearby, I mess with it's in a pair of rings, and I can move the guide scope around anywhere I want. So I've never had to worry about that. Okay, interesting. Okay. Um, Now problems I had with taking images, these are the problems you've probably all heard of before. The wind comes around, shakes your scope. Nothing you can do about that. Um, Pretty much the issue there is the longer the exposure time, the more likely you're going to have a wind gust destroy your image. Um, Then the second one is something I called atmosphere turnover. That was an interesting one that I had to figure out what was going on. And it's probably unique to desert environments. Um, I was on top of a ridge, um, was the site I did a lot of my deep sky work when I first moved here, was a place way out by Catalina. There was a nice ridge that I would get up on that had really good dark skies and everything. And there was a valley below me. And what I found is that after sunset, half hour, 45 minutes to an hour, I'd feel this warm breeze roll up the ridge from the valley beneath me. And it would only last for a few minutes. And it was very predictable. I got to where I knew, okay, until that happens, I can't do any photography and it's going to take about an hour. It turns out what that is what's called atmospheric rollover. During the day, the surface of the ground gets very hot, and you get a lot of warm air close to the ground from the hot ground. But then when the sun sets, the air cools off, and you got this hot air near the ground, and especially in a valley, you get this turnover where the hot air finally rolls up the valley and the cold air comes down and sinks into the valley, and you get this this turnover breeze for a few minutes while the atmosphere does its thing, and then it settles down again and everything is fine. Um, and then I actually did a study. I did a lot of astrophotography when I first moved here with film, and I did a study and I actually started doing statistical analysis of my pictures out of a roll of film. How many successful pictures did I get, and so on and so on. And obviously, fatigue is a problem. You get tired of looking through the guiding eyepiece and pressing the buttons on your control. And what I found was that I could only do about 30 minutes and get good results. And after that, and when I started getting to 40 minutes and 60-minute exposures, my failure rate went up dramatically fast. And I found that I'm just getting tired. So I found that if I wanted to if I wanted good photographs and I wanted to do it in a short exposure time, like 30 minutes or less, um, I needed to go with those high-speed films. Otherwise, I couldn't get the exposure times down. So again, there's that trade-off. But this is what I saw with my results. It's like, wow, look what happens at 35 minutes. Things go bad. And at 60 minutes, I found that when I got to where I was trying to do 60-minute exposures, I found that I was losing more than half of my pictures because of fatigue. I'd get tired and I wouldn't press the buttons fast enough. I'd see the image move and I'm just not quick enough on the buttons to keep it back centered, and I'd screw my image up. Oh. All right, and polar alignment. Okay, if you're going to do long exposure, even with digital cameras, I guess you need to have a properly polar aligned scope. I'm not going to talk about how I do it. Blah, blah. Blah, blah. Polar alignment. I don't think I need to go into that. Most clock drives you can adjust the speed on. I always have to check my clock drive speed when I take my scope out to do photography because it might not be set properly. It it has a default setting. I found with my scope anyway, the default setting on the clock drive is 360 degrees in 24 hours. That, surprisingly enough, I found is the default setting on a lot of clock drives. And it has to do with the gear ratios and the motor and everything, but you can figure that out. You can do a count on the gears and the count on the gear teeth and all of that, and you can figure out what the clock drive speed is going to be. 360 degrees in 24 hours is not quite the right rate because we know that the sidereal rate, it should be 23 hours and 56 minutes. So I found that I had to speed my clock drive up a little bit, which I'm grateful that I can do that because on a lot of clock drives you can't adjust the speed. Most of them I think you can, but there's some where you can't.
I'm not sure what scopes today would allow that on their drive systems, at least from the current manufacturers, maybe on the older ones. But it also gets into a very niche set of settings that were probably buried underneath like 11 million menus. So who knows?
Well, and here's the other issue too. If you're doing digital photography and your exposure times are relatively short, this difference doesn't amount to very much, okay? And this difference is probably within your ability to correct for it if you're doing auto guiding. Your auto guider will probably pick this up and correct it. Okay, so that would be one advantage to auto guiding is the auto guiding would probably take care of that for you. But if you're doing manual guiding, I don't, you would be pressing your buttons a lot if it was running at solar rate instead of sidereal rate. You'd be pushing the button every 30 seconds to try to keep the thing centered. So like I said, I'm grateful that my clock drive allows me to change the speeds, but I'm 99% sure that whenever I turn my clock drive off and then turn it back on, it comes up at the solar setting. I think that's just the default setting, and it's like I have to go in there and manually adjust it. Um, but it's nice to be able to do that. So that's something to think about if you're going to do photography is what's your clock drive running at? Um, that's it. That's everything I got. I need to update this presentation with new stuff, but
Did you want to show off the
2018.
glass slides now that you're done? You'd mentioned.
Oh yeah, the glass slides. Oh yeah, let me stop sharing and I can at least give you a peek at them. They're going to be a little bit hard, but all right. So this, let's see if I can do this.
And I do have you spotlighted, so everyone should be
Okay,
able
so
to see.
let's get it up to the camera. So that's a glass slide that shows a spectrum of a star, and you can see all the lines and things there. It's not well focused, but that's the best I can do. Um, oh, there it is. So there's the spectrum, and that's on a glass plate. And this particular glass plate is 115 years old. Um, and let's see, there it is. There's a glass slide of the Ring Nebula. That's not bad.
Little dusty.
Yeah, no, those are stars. It's not
Oh,
dust.
it seems like it's more like surface dust sitting on the glass from
Yeah,
the way the
no,
camera was
those are
catching.
background stars. That's not surface dust.
Uh,
This also is a 1910 image, so it's 115 years old. And then I'll do one more. I had like 10 of these when I first did this. I don't want to show all those plates. To get them
I
right.
would show the one, if I remember correctly, you had one of the whirlpool,
One of the what?
the whirlpool galaxy.
Oh, yeah, I've
If I
got
remember
one.
correctly, you had one of those.
Yeah, I can find it if you want to wait a few minutes.
Uh, but you don't have to. I just
Okay.
making a suggestion.
And then this one is some globular cluster. M13. Oh, I got it backwards. Not that it matters. Astronomy don't care about left and right. So this is let me get it in the camera right there.
It's
M13. Oh, that's not
it's
right.
coming in and out of focus and exposure because the camera's trying to
Yeah.
adjust. So.
But anyway, so yeah, I've got some of these vintage plates that I found online. Um, Surprisingly good photographs of some of these objects for being over 100 years old.
Thank you very much, Doug.
Any questions?
no, Doug, great presentation. Thank you.
Very
Doug.
informative.
And if not getting a lot of questions for Doug, P, I guess we'll go ahead and kick it over to you for Pisces.
Okay. Do, do, do. Share. Everyone see the first slide?
Yep.
Okay. Just got to move some things around here. Get them out of the way. Oh, nope, didn't want to do that. Oh, great. Got one of the bars right in the center of my. There we go. Okay. Hey, good evening. Thanks once again. Appreciate your all's attention. This is only an hour and a half presentation, so bear with me. No, this shouldn't go much more than 20, 25 minutes. As big as Pisces is, there's not a whole lot about it unless you really want to go down rabbit holes and deep dive into some of the objects. Yeah, it's got a lot of stars. But anyhow, I will start off without further ado. And by all means, if you have a question, you see something isn't quite right, and you know something about something on one of my slides, please speak up. Okay, constellation details. Northern sky. Right now, Pisces is basically, an hour ago when it first came up and it was dark enough out, basically sits pretty much in our eastern sky. But it's pretty much a northern sky zodiac constellation. It's generally highest in our skies early August in the early morning, and then in January it'll show up in the early evening. That's why we see it now, pretty much in between those two times. rising when it gets fairly dark out. And of course, it's going to progress. Probably in a couple hours, it's going to be in our southern sky, and a few more hours at that. Early morning, it'll be setting off to the west. Basically, when it is south, it will sit. It can be seen between 50 and minus 80 degrees. I'm sorry, 50 to 80 degrees above the horizon, above the horizon is where it'll be visible. So Pisces is known as the fish, Latin derivation. Neighboring constellations, Andromeda to the above it, Aries and Triangulum will be off to the left. Aquarius off to the bottom right, Cetus below it, and Pegasus just above it also. There are no first magnitude stars. The brightest stars in Pisces are 3.83 or less, and I think there's just a couple of them. So it can be rather difficult, especially in suburban skies, to pick the constellation out. If you're in dark skies, of course, it's going to be much easier. It's 14th in size out of the 88 recognized constellations, 889 square degrees. It does have one meteor shower associated with it that peaks generally between September and October. The Pisces, not real well known. I don't know if anybody's ever sat out there and looked for any meteors coming from it or actually tallied any survey of the shower during late September, early October. Uh, Here now, it can be seen between the latitudes, basically from the North Pole all the way down to 65 degrees below the equator. There are 9 named stars, 10 stars with known exoplanets as of, and I think this is pretty current up to this year, and only one Messier object. Of course, you would expect that. It's way off the side of the Milky Way, but M74 is the only Messier object, deep sky Messier object. You can see the constellation. Can everybody see my cursor moving around on the display on the my PowerPoint?
Yes.
Oh, okay. So basically, you've got Pegasus sits up. You can see the square of Pegasus, and Pisces basically runs from the northern part of the fish, and I'll explain that. There's a couple of asterisms or groups associated with that, but runs down here and over to the right, and I think the circlet is right about here, which is the other end. So this is basically the way the constellation runs. If you're really good, I'm sorry, not over that far down this way, because this is actually Aries here, and here's Triangulum. And like I say, you can see the box of Pegasus there. Now we can see it a little bit better in the diagram, but you can see how there's a, the constellations emphasized a little bit more in this photograph, but a little bit about its history. And it's sort of a mix because it depends. The Babylonians actually figure in here twice, going back to the first millennium BCE. In other words, the old BC. We're going back 1,000 years before AD. Babylonians at one point identified this particular constellation, not in its current form necessarily, as the swallow. And it marked a position in the year when the swallows returned to northern latitudes, probably when they came back to their areas that the Babylonians were living in. The constellation in its basically current form was first cataloged by Ptolemy in the 2nd century CE, Common Era. Latin translation, like I said, is the fish. There's another association, Babylonian origin, as a pair of fish joined by a cord, which becomes common, and this was pretty much carried into the current form of the constellation. There's a Roman myth associated with this particular constellation that Venus and Cupid were transformed into fish to escape a monster, Typhon. There's a similar story in Greek mythology, so they do share a little bit of that. I don't know if you want to call it legacy or background. The vernal equinox in the spring is located in Pisces. So what happens is on the first day of spring, as the sun crosses the equator, it will actually occur in the constellation Pisces. It is the second dimmest of the zodiac constellation, so it is at times can be very difficult to make out. Yeah, we all know where it is, but as far as trying to make out those individual stars, generally the circlet isn't too bad because you can see even in this photograph, there's a fair number of relatively bright stars, but like I say, most of them, nothing's, they're all 4th magnitude or less. Now, going back to the 1690s, there was an astronomer by the name of Johannes Hevelius who sectioned Pisces. And, I think I've talked about asterisms before, which are groupings of stars. For instance, Ursa Major is a constellation. The asterism inside Ursa Major is the Big Dipper. A lot of the well-known constellations have asterisms with them, and some of them, it may be just part of a constellation, or it may be something completely different. Not even necessarily a part of a constellation, but it may be in the one. But in this case, Johannes sectioned Pisces into 4 asterisms, and it's pretty easy to see. You have the Pisces fish Boreas and Astrinus, which north and south. So you have your north and south fish, okay, the circlet. And then you have Linium, the cord, and this is common in the mythological story about Pisces, but you have the Boreum and Astrinum, which the north cord and the south cord. So, and these are the groups, and this is a pretty common sectioning of this particular constellation, given especially its size. Getting to some of the specifics, some of the notable stars, and I apologize because my little chart is not very clear. I'm not going to try to identify everything on the chart, and I can't find my other guidebook, but just highlighting, and I'm not going to go through every single one, but you can get a general idea. Like say, Eta Pisceum, Elford is one of the name. In Arabic, it's spout or the outpouring of water. It's a yellow giant. You can see the classification there, and I have the classification chart at the end of the program if you want to compare that. Apparent magnitude of 3.83. It is the brightest in Pisces, so nothing really very bright at all. It's 350 million light years from our solar system. This particular star has a mass 3.78 times our sun. The radius is over 26 times greater and luminosity is 457 times that of our sun. And the temperature is, I think, quite a bit cooler at just under 5,000 Kelvin. It has a 7.5 magnitude companion. Combined, they come out at 3.61. And the yellow giant in this case is estimated to be about 220 million years old. Typically, I don't know how much, it's not that much bigger than our, being that much bigger than our sun. I would expect that we generally look at ages for these types of stars in the hundreds of millions of years, more than likely not billions of years. The second brightest star in the constellation is going to be Gamma Piscium. It's a yellow giant also. Apparent magnitude 3.7. You see very similar numbers. They do vary a little bit, but it is significantly larger and more luminous than our sun. It is part of the circlet, so it's off to that. And I think in this case, oh gee golly gosh, if I'm not mistaken, I think it's either here or there, but it's in the circlet off to the far west. Iota, yellow white dwarf. Omega, another yellow giant. And you'll notice that, for the most part, a lot of these are relatively close. Some of them in the hundreds, just over 100 or less light years away. In some cases, you look at Iota, it's only 44 light years away. So some of these are relatively close to our solar system. Oresca, Arabic for the rope, which is alpha. Here we have one. This is 4.33 in magnitude, but it's a close binary. The primary is an alpha 0 Papa. The companion is an alpha 3M. You can see the relative size of that. They're not, double, 3 times the size of our sun, in some cases 30 times the luminosity. The period of this particular binary is in excess of 700 years. Let's see. So Epsilon Piscium is an orange giant, larger and more luminous than the sun, 182 light years, and suspected of being an occultation double. In other words, the two stars actually pass in front of each other. I'm not sure on the relative sizes whether they, I'm going to guess occultation, since they brought it up, they're probably similar in size and may actually block each other at one point. But, and I don't have the period, I'm sorry. Theta is another orange giant, larger than our sun, but cooler in this case. I like this one. Well, Fumo Samaka, Arabic for mouth of the fish. So I'm going to guess it's going to be at one of the ends. It's Beta Piscium. This one's a little bit further away, almost 500 light years near. Interesting one here that's relative, and I'm trying to remember. Yeah, relatively not that far away. It's only 14 light years away, but Van Manen star was discovered by Adrian Van Manen in 1917. It's a white dwarf. It's believed to be a metal star, elements heavier than helium. Most stars, generally the younger stars, very common stars will have hydrogen helium, but this one is believed to be beyond helium. It's the third closest dwarf to our sun. Uh, let's see, 12.3 in magnitude, so not all that bright, but like I say, only 14 light years away. The mass is about 60% of our sun's. The radius is only about 1% of our sun's, and it's estimated to be 3 billion years old. So not quite, far from being as old as our sun, but it's probably going to live for some time to come if it doesn't meet a cataclysmic end. Okay, I think that's it for the notable stars. Maybe. Oh no, there's always a few more. And I'm not going to go through all these. I'm just going to hold this slide on a little bit, just so one of the neat ones I really latched onto right around was 19 or TX Piscium. It's a carbon star. It's red, and I'm sure it's one of the things. I did the carbon star program over a year ago, and I'm sure that it's one that I would have latched on, especially given that it's one of the reddest stars that we can see. It's kind of neat when you look at these kind of stars. Even with my old eyes, some of them are very distinctively red, and they're kind of interesting to look at with that type of color because I generally can't make out, for me, much of the difference between white and yellow. When we get into these red and orange stars, it's very distinctive in a lot of cases. And then in some cases too, like 107 Piscium, uh, stars have moved around in the constellations a little bit, not so much because of their relative motion, because of the changes in the boundaries. In this case, this particular star was associated with Aries, and being that Aries is right next to it, sometimes stars will move, or you'll find a star in one constellation with a numbering designation from a neighboring constellation. 54 Piscium, it's an orange dwarf, 36 light years away, so not that far, but it had an exoplanet that was discovered in 2002, and it has a brown dwarf companion that was discovered in 2006. This was the first brown dwarf discovered with an exoplanet. The exoplanet is believed to be about the size or the mass of Saturn. However, it orbits very closely. It has a Mercury-type orbit, and if I remember correctly, it's roughly 58 days going around its sun. I can't remember exactly what Mercury's is, but it's
88.
88. Okay, so on the same order, but as far as distance, very similar. And then we have 6G, which is a yellow subgiant, two exoplanets. Kind of interesting, not so much on, this star is somewhat similar to our sun. Two exoplanets have been discovered in it. One has a period of 7 days, the other one has a period of 8 years. How they were able to figure out the 8 years at this point, I'm not entirely sure. I can get the 7 days, especially if it's going in front of the star.
My guess is that they detected that from radial velocity shift rather than
Oh,
from the
okay. Yeah,
transit
that's right.
method.
Okay, that makes sense. Thank you, Connor. Yes, that makes a lot of sense. So, being able to detect something with that long of a period. Now that does finish the stars. Any questions? Any comments? Any inputs?
Question.
Yeah, go ahead.
Back one slide.
Sure.
Um, Maybe even one more slide back.
The first one. Okay. Yep.
Gamma Piscium.
Yes.
Are you sure about that movement? 75 arc seconds?
Oh
It's,
no, that's
it
a
looks
point 75.
0.75.
Point
.75.
3/4. Sorry,
Three
three
quarters of an
quarters.
arc second per year. That's really fast.
Yeah.
You sure
No, that's
about
right,
that?
because that's going to be on, well, like I say, it's almost an arc second a year, so it's going to show up.
That's quick. I mean,
Yeah.
that
I mean, it's
seems
not as
almost
quick as, Barnard's is a little bit quicker than that because that'll do what, 2 or 3 arc seconds in a year?
okay.
Yeah.
I'm surprised at that. That's a fast moving star.
Yeah. No, it is. You're absolutely right. Good pickup.
Okay.
Can I test to it 100%? No doubt. That's what I seem to
No,
recall from my notes, but yeah.
okay.
No, I understand the comment. Makes a lot of sense. Okay, moving on, deep sky objects. Here we go. The first one is the one Messier object, the Phantom Galaxy. It's a spiral face on. That's the photograph you can see immediately to the right. It's a very nice looking spiral. It's a classic spiral, probably in the sense that most of the average spirals are low surface brightness. It's difficult to observe in amateur telescopes. I can't, apparent magnitude of 10. I don't see why, but evidently it is, according to the sources. Over 100 billion stars, or approximately 100 billion stars, discovered by Pierre Méchain. Two supernovas were observed. Of course, with typical supernova nomenclature, it's going to be SN, then you're going to have the year of discovery. I'm going to leave it up to anybody that has input on the small letters after the supernova designation, the AP and the GD as far as meaning. But the first one is one of these rare 1C types, hypernova, much higher energy than most supernovas, which, kind of interesting to say. Possible origin of long duration gamma ray bursts, and these are gamma ray bursts. And I think this one has jets that go out to over. No, not the supernova. That's something else. I'll get to that later. And then there was another one discovered the following year. Anybody have any inputs on those designations after the year?
I
I think
believe it's just a regular incrementing of numbers where they go like
yeah,
A to
that's what I
B to
was gonna
C, and
say.
then
I
they just
think
wrap
Oh,
around.
okay. Oh, I got you. Okay, that makes sense.
It's not like an actual code for the designation itself, rather than just astronomers are lazy, but they still like to have things categorized.
So
A,
it's
A,
conceivable
A,
that they discovered a few dozen
oh, they do.
supernovas in 2002.
They discover many. If you think about other galaxies,
You're right.
all the other galaxies, they see many
Okay.
supernova each year. Because
Okay. So it's just an added designation for
yeah.
the ordering of them.
Now the fact that there was two of them in back-to-back years, that's kind of unusual.
Yeah. There's also, and this is, let's see, no, this is not the image that I have there to the right, the M74 group. So there is a group of galaxies, about 5 to 7, that are maybe associated with the Phantom Galaxy. M74 is the brightest, and these are basically smaller irregulars, nothing nearly as dramatic as spiral that are within the neighborhood. However, and this is an interesting one. This is a galaxy cluster, and that is the image off to the right that was taken by, I believe it was by Hubble not too long, just a
That
few
looks
years
Hubble.
ago. Yeah, but you can see it does show some lensing, but it's a galaxy cluster, and you have quite a few yellow ellipticals and spirals and lensing. Uh, there's believed to be a galaxy behind that that was indicated by the lensing, but here we have something a cluster on the order of 3.6 billion light years away.
I would
That
also
gets
not
to
expect that galaxy cluster to be visible in reasonably accessible optics for amateurs.
Oh yeah, no doubt.
Definitely
This
not.
this is definitely a Hubble image. So and yeah, the galaxy behind, of course, is estimated to be 5.7 billion light years away. So a couple more billion if you want to add it to that. But I thought this was a pretty dramatic image, especially since it showed the lensing effects around this cluster. A couple of other deep sky objects, NGC 7541, a barred spiral. That is the photograph right next to it, top left. Diameter, well, it's 103 million light years from us. The diameter is 125,000 light years. It's paired with a neighbor that is not in this particular photo, and it was discovered, of course, by Herschel in 1785. And I think the one off to the right might be, yeah, that's its paired neighbor, a little bit smaller version to the outer right is 7437, a spiral galaxy with an apparent magnitude of 13.9. Another interesting one, the Bullseye Galaxy. It looks just like a bullseye. It's kind of interesting how some of these actually look like their names. But this is sort of a unique type. It's called a collisional ring galaxy. It's actually a classification, CRG. It's 434 million light years from us. It has 9 very distinct rings, more than most other spirals. In fact, this may be one of the record setters. It's theorized that a smaller dwarf galaxy passed through the center of this much larger galaxy, creating the ripple and star formation. So I would imagine it probably either came through the top or the bottom, pretty much at a 90-degree angle. In other words, wouldn't have been glancing to leave such a symmetrical pattern like that. But that's what created the ripples and the star formation in this particular galaxy. This is discovered by the Hubble in 2025.
This galaxy itself or the additional rings? Because it seemed
The
like
the galaxy as it is right now, that's how it's imaged.
no, as in like this way when it was discovered.
Yes. Not
Hmm.
quite sure what you're asking, Connor.
So yeah, oh, there's this ring structure discovered. Okay. With
Yeah,
the way you
well,
said it, it's like the Hubble recently discovered this galaxy. I'm like, wait, it threw
well,
me
I think
first.
that as far as drawing out the image and being able to see these rings, from what I understand, yeah, the ring structure was discovered by Hubble in 2025. So that was one of the first times that this one was imaged. Yes, no, as far as
I'm picking on phrasing. Continue.
okay.
You're fine.
And then we've got a couple of more. NGC 383 is a double radio galaxy, 209 million light years away, quasar-like active, supermassive black holes believed to be at the center. And then there are a number of other NGC items that are associated in the nearby area, but not nearly as dramatic looking as this particular galaxy is. Another spiral in the center, apparent magnitude of just over 15, 400 million light years away, two neighboring galaxies. Of course, the star you see there is probably much closer to us in the foreground of these two particular galaxies. And then there is one, the Pisces dwarf. It's an irregular dwarf galaxy. To me, it looks more like somewhere between a globular and an open cluster of stars, but it is a dwarf galaxy. The apparent magnitude is only about 14.2. It's 2.5 million light years away from us. Possible satellite, and I cannot see the rest. There it is. Possible satellite of M33. Most of the stars are believed to be, and this is, we're getting 8 billion years old. So, uh, getting to the point where, and I think that's where we have the Milky Way galaxy at. Yes, approximately 8 billion years, or a little bit older, maybe. Go ahead, Doug.
What's a double radio galaxy?
Good question. I don't know, other than the fact that I think this is the one that is putting out massive jets on either
And
end. You
two
can't.
radio sources.
Oh, okay. But it puts out some massive jets going out either end that are on the orders of light years in length. That's how far they go out. But these are some of the most active from standpoint of putting out energy and in this particular case a lot of radio energy, but I suspect a lot of other energy in different wavelengths. But they're very active, putting out a lot of energy, along the entire spectrum in some cases. And some more. 7714 and 7750. Oh,
I
go ahead,
gotta
Doug.
go, Pete. I gotta check out for my
Okay.
8 o'clock.
Hey, thanks, man. Take care. Have a
All
good
right.
night.
Good night, everybody.
All right.
These are two interacting galaxies. You actually can't see 7715. I wasn't able to find an image of that. But a spiral, there's an edge on spiral irregular that is outside this picture. There was a supernova discovered in 1999 that was discovered in 7714, the galaxy that you see in the image on the left. NGC 474 is a large elliptical. I thought it was kind of an interesting. It has tidal waves. Nothing on what might have caused these tidal waves. Obviously, whether it was something that came through this particular galaxy or something happened to it internally. Well, here again, another Type 1 supernova back in 2017. And then I think finally, which this is one of the more interesting pictures I saw, I thought it was kind of interesting. The Flying Ghost is a pair of interacting spirals. When that happened, I don't know. It's probably been some time with a pair of magnitude of 12.2, 90 million light years away. Uh, Heavy hydrogen 2 nucleus, so there's a lot of gas in there. You can see a lot of the dust too, but kind of a pretty spectacular image from one of the deep sky images in Pisces. These are my references. Of course, I always include my HR diagram if you want to look at the different types. Thank you very much for your attention. Any questions, comments?
Awesome.
Thank you.
You're welcome.
Great job, Pete.
And I will stop sharing if no questions. And it's back to you, Connor.
Thanks, Pete.
You're welcome.
So
It was kind of weird getting back into a constellation. It's been a couple of years. It's been astronomers and programs over the past couple of years, I think, that I've done.
yeah. Well, thank you, everybody. I think we'll go ahead and call it a night here. I think forward to seeing more of you back next month.
Okay, thank you
Yeah.
all. Take care.